this video, I will discuss a class of ordinary differential equation solvers, namely Runge-Kutta methods. Now, mind you that this is not explicit exam material, but I find it is important that I tell you at least something about Runge-Kutta methods because they are, let's say, the go-to methods when you're faced with standard problems in practice. So at least we should have a small chat about these Runge-Kutta methods for this course. Now, Runge-Kutta methods, there is no single Runge-Kutta method, but rather they are a family of single-step methods, which are in the form of as follows, such that we have that the numerical solution in the next step is the solution in the current step plus the step width times a slope. And we've seen that actually all the methods we've seen so far, they fit this this description. They were, let's say, invented by, or this framework was invented by Karl Runge and Martin Kutta, two German mathematicians in the late 19th, early 20th century. Now, this slope that we use in order to update the solution to the next step is a linear combination of different slopes from multiple stages, from S stages, where S can be 1, 2, however many you want. And then we can, so we can rewrite this slope over here as a linear combination of slopes Ki with coefficients Bi. And these coefficients Bi and the slopes Ki are then determined in order to obtain a maximal accuracy. So higher order methods are attainable using this Runge-Kutta frameworks. So just writing this out explicitly, well, we can write it like this, so that the solution in the next step is the current step plus h times this linear combination of slopes. And so really many methods fit this description. So many methods fall into a certain class of Runge-Kutta methods. So for example, the first method that we discussed is explicit Euler. And explicit Euler, well, there we have as an update to the solution h times the slope evaluated at xi and yi. This can be simply rewritten as a single stage, first order accurate explicit Runge-Kutta method, where the coefficient B1 is 1 and the slope K1 is simply f evaluated at the current solution step, so at xi and yi. So explicit Euler is a single stage Runge-Kutta method. But also, for example, modified Euler, which can compactly be written as follows. Well, that is a two-stage and second order explicit Runge-Kutta method, where the coefficients B1 and B2 are both equal to 1/2. And the first slope K1 is f evaluated at xi and yi, so that's this similar slope to explicit Euler. But the second slope is f evaluated at xi plus 1 and at yi plus h times k1. So we see that if we enter this in here, well, we recover our original modified Euler explanation. How to interpret this? Well, for that you should rewatch the video on modified Euler. But here we see that we have a linear combination of two slopes, K1 and K2. They are averaged, and that is the slope that we use to update the solution then. Now, there are many possible and many common Runge-Kutta schemes. You can actually come up with an infinite amount of Runge-Kutta schemes if you want. You can keep on adding more and more stages. There are Runge-Kutta schemes of relatively low order, like this explicit Euler, which is first order, but they can go up to very high orders of accuracy. You have explicit Runge-Kutta schemes, implicit Runge-Kutta schemes. So there's really a wide range of Runge-Kutta schemes in literature. However, explicit Runge-Kutta fourth order is in practice probably the most important method out there. The most important method for solving initial value problems is probably Runge-Kutta 4. Even so that when people talk about the Runge-Kutta method, they talk about Runge-Kutta 4 explicit. So this explicit Runge-Kutta 4 is really the go-to method for all your standard problems, all your standard initial value problems. How does it look? Well, it's a standard Runge-Kutta method, so we have this equation which partitions the x-axis. There's nothing too special about this, but our real equation is as follows. So we update the solution to step I plus 1 from the current solution by using a linear combination of 4 different slopes, k1, k2, k3, and k4. And k1, k2, k3, and k4 are chosen as follows. So we have that k1 is simply the slope that we would use in explicit Euler. So that's the slope evaluated at the start point. Then we have 2 different slopes that are evaluated in between xi and xi plus 1. So they're evaluated at the midpoint. And the y coordinate where we evaluate this one, well, that is, let's say, a half-width Euler step with the k1 slope to obtain slope k2, or a half-width Euler step with the k2 slope to obtain slope k3. And then finally, we do yet another Euler step with k3 slope to obtain the coordinates where we evaluate f over here. So you see that, well, in order to do one single Runge-Kutta step, we evaluate f 4 times, and we compute quite some points in the meantime. So we compute 4 intermediate points in order to do only a single actual update to our numerical solution. So let's take a look at how this actually looks like in practice. Also, a small note here is that if the function f is not a function of y but only a function of x, then your initial value problem basically boils down to a numerical integration problem, and then Runge-Kutta 4 is equivalent to Simpson's 1/3 method, and you can verify this yourself. It's maybe a nice exercise. It's rather straightforward, but anyway. So how does this Runge-Kutta method look in practice? I show it here. Let's say that we have an analytical solution as shown by the blue curve over here, that we have a direction field as governed by the gray arrows over here, that we want to do a Runge-Kutta step for h is 0.8, and we want to, well, apply Runge-Kutta fourth order. So we want to compute 1, 2, 3, 4 slopes in order to update the solution to the next time step. So let's take a look at what this looks like in practice. So here we have our point xi, yi, or the current numerical solution in step xi. So what we do is, well, we compute k1. K1, that's simply f evaluated at xi, yi. That's this horizontal slope in this case. Now, in order to compute k2, well, we will have to compute this at xi plus h over 2. So that will be at x is equal to 0.4. And at yi plus h over 2 k1. So in order to do this, well, we draw this line a bit further. We check where this crosses x is 0.4. And this is the point where we evaluate f in order to obtain k2. So that is k2 will be this slope over here as shown in green. Okay, so we have k1 and k2. Let's move on to k3. So for k3, well, we evaluated at xi plus h over 2. So again, at x is equal to 0.4. But at yi plus h over 2 times k2. So what we need to do in order to find k3 is, well, we need to draw a line from xi, yi with slope k2. That is, let's say, this dashed slope over here. And then look at this line where it crosses x is 0.4, and that will be this point over here, and that is where we again evaluate or we sample the direction field to get another impression of what this direction field looks like in order to compute our weighted average of these slopes that we actually use to update the actual solution in the final step. So we compute K3 over here, and that will lead us to have this purple slope over here, which is counted twice actually in the Runge-Kutta update step. And then finally, in order to find K4, well, what we do is we need to evaluate it at x2, so x1 plus h is x2, and at a y coordinate of y1 plus h times K3, so that is this line. We draw a line with that slope over here. So this means that K4 will be obtained by evaluating f over here at this point. So now that we have found these four slopes, K1, K2, K3, and K4, this gives us, as you see, a nice sampling at different places of the direction field. So that's also what allows us to obtain such a high accuracy, is that we can check, we can probe a bit how this function f of x and y looks like in the interval from x1 to x2. And then we compute some kind of an average, a weighted average of these four slopes that will result, let's say, here in this black slope over here. And then we can apply this final step. So this is the black slope is, let's say, this sum divided by 6. And then we just say yi plus 1 is yi plus h times this black slope. So the Runge-Kutta solution will be over there. So that is how Runge-Kutta fourth order works. Now let's take a look at how this compares to the other methods that we've seen so far. So comparing, let's say, Runge-Kutta 4, which has a fourth order accuracy, for our go-to example initial value problem, which had this exact solution of e to the power x squared over 2, we see that, well, it does very well. So the yellow dots are the Runge-Kutta solution, and you shouldn't look too much on the dotted lines. They're just there for visualization. What actually matters is where the markers themselves are. And we see that for Runge-Kutta 4, for a spacing of h 0.4, the Runge-Kutta 4 solution is basically indistinguishable from the exact solution, whereas the first order methods, implicit and explicit Euler, are way off. The second order methods are relatively close, but start to deviate somewhat near the end of the interval, as these truncation errors, they grow exponentially with the length of the integration that we're doing, as we've seen. But Runge-Kutta 4 is really not hindered by this so far because of its high accuracy at x is 2. It's still virtually indistinguishable from the exact solution. However, I think even more astonishing is if we take h to be really, really coarse. Let's say that we take an h of 1. So we only take 2 steps in order to reach the end horizon of our integration of the differential equation. And let's take a look at how the, let's say, more accurate methods perform here. And we see that the second order methods, well, they really start hurting because of this large step in h. We're really quite far off from the exact solution by now. Whereas Runge-Kutta 4, again, these dashed lines are more kind of a visualization. What counts is where the dots, the markers themselves are. Runge-Kutta 4 is basically still very close to the exact solution. So this is really the advantage of these high order methods, is that you can take very large time steps and still get quite a decent solution accuracy.